This podcast is brought to you by HEC Paris.
Okay, great. Eric, thank you for your introduction. I mean, certainly I'm very happy, so we'll soon be very happy to map, such a small place like Princeton to Paris. Certainly it's a very glory map for us. Okay, so first I would like to thank organizer Rohan and Veronica for inviting me here. Actually, I have passed by Paris a number of times, but rarely got a chance actually to see our Paris. So this time actually I have some time spent here, so it's wonderful weather. And I was a little bit worried myself about the afternoon talk because it's a little bit tough for somebody come from America. But since after lunch, no, it's a challenge from both parties, so it's fine. So my talk today is based on the work with Yin Li, my postdoc before, and Kayu, my PhD, former PhD students. So I think it's about 5:24, 25. Just I don't know, maybe my watch doesn't but give me an idea what it is. All right, so what's about the talk? So basically, I'm trying to ask myself how to select sparsely optimal portfolio. So if you have, let's say, 1,000 stocks, how do I select some of those to invest? And that's what I mean by sparse. And the main question today is how to use high-frequency data to shorten the time intervals. We have lots of funds with high-frequency data, and I was trying to see if there are any, through the concept of practical utility of high-frequency data for risk assessments, and how large the universe of assets can be handled. And, well, how does the estimation of vast covariance matrix impact on the allocation vector as well as portfolio risk? So these are basically the questions I attempt to answer, and some of those I probably could go more deeply. Some of those probably would be just heuristic mathematical arguments. So here's the outlines, introduction, usual suspect, portfolio selection, with time-varying covariance, and then covariance matrix estimation based on high-frequency data and empirical studies. And again, I could present you a simulation study, but you expect if everything's doing right, there's no reason mathematics is wrong, so simulation study will be the same, but just quantify what I have said using mathematics. So the fifth part, maybe I'll skip due to time constraint. All right, so this is the standard traditional Markowitz mean variance theory. So you're trying to minimize portfolio risk subject to certain constraint. Let's say target return is R0, and the solution certainly is very trivial, simple quantitative programming problems. And this is really the cornerstone of modern finance. And even though it's a lousy, well, it's not quite realistic, but still so handy and so easy. So many people still use different versions of this kind of portfolio locations. However, in practice, it is always too sensitive to input vectors such as the expected return or volatility matrix. And the problem is certainly getting more serious if you are consider a large portfolio. So for example, if you had 2,000 stocks, then in theory you have 2,000 by 2,000 covariance matrix, which involve 2 million elements. And we really don't know estimation error aggregate or cancellation. But if you're thinking that in the usual case, the worst scenario, error aggregate, then error aggregation of 2 million estimation error could be huge. So as a result, it is not very well understood. That is, using this morning's terminology, this is econometricians measure a risk based on the data, and the oracle or the god know the risk is without sigma hat there. So the difference can be quite large because you involve 2 million elements, estimation of 2 million elements. And similarly, this is the allocation vector you get based econometrician based, and the oracle based or God based is this. So that can be quite different too. And so one way to resolve this kind of problem is to make portfolio more stable. So one way to make portfolio more stable is that you put just extra L1 constraint there on your portfolio allocation vector. And it's not like particular I like L1. Actually, many people who know that I'm doing models high dimensional theory a lot. Actually, I don't like L1. But L1 here appears just naturally have financial economic meaning rather than mathematical meaning. So by putting L1 here, because the positive part allocation and negative part allocation is L1 mon, no more than C, and then plus the total allocation is 100%. It really implies that you have constraints on the short positions, no more than C minus 1 divided by 2. So in particular, the smallest C you could get is 1. That is no short sale portfolio. So you have optimal no short sale portfolio on one hand, and as you relax the C, you progressively got a very large family, and C equal to infinity is like conceptually like Markovit's original type of problem. So we're really creating a solution path specified by risk control parameter C here. And the solution here is usually sparse, meaning that many of those W's who have allocation weights exactly 0, and the concept certainly apply to many measures. And the W here actually is also A matrix here also arises naturally. For instance, the A here could be the expected return equal to 10%, but more than likely, I mean, in certain mutual funds or in allocation, you may say, hey, I want my portfolio to be risk neutral, right? So you have, you automatically have a vector A. You maybe want to be risk neutral with respect to certain factors. You have some constraint A's here. So what the quick thing is that the more A you get there, I mean, actually you also imply some kind of constraints on L1 mon of the C. So the most fundamental thing is now is the stability produced by this constraint here, or actually produced by this. So in order to answer this question, from now on, I will just drop the constraint on A's. So here's the risk approximation. So let's say this is the utility or expected log utility function. And so this is the log utility function that God knows. And this is the log utility function that econometrician being able to get. And now the question is how much the error are there? And this is a very simple mathematics. You could easily show that if there's a constraint on allocation, on percentage allocation that L1 mon controlled by C, then actually there's no noise accumulation effect. Actually, it is the worst estimation error that control the upper bounds. Okay, so for example, if C no more than 3, then all those constants here is limited, and in addition, I mean, C more than C equal to 3 is quite large. That means you have 100% short and 200% long portfolio is already very skewed. And this, of course, the whole theory here doesn't apply to any size of portfolio, whether P is bigger than sample size N or less than sample size N. And as a particular, if I just consider risk rather than utility, which is what I'm going to focus on now, then we have a simple risk approximation. That is, this is the econometrician risk, which you could compute, and this is God risk or Oracle risk. You cannot compute, but is bounded by the maximum components y estimation error times C squared. So this is basically the simple one. So let's look a little bit, just introduction, a little bit on risk approximation theory. So so this is the Oracle risk using true covariance matrix, and this is the empirical risk, the econometrician risk that are available to you. So this is the ideal allocation vector you wish to get, and this is the econometrician's allocation vector according to the data, the best you can do. And so therefore, I got 3 quantities, and one quantity is the Oracle risk. This is most ideal. You put your allocation vector into the real market. Without an N here is the Oracle ones. And this is the empirical one, so you put in things into what you know. So this is empirical optimism. And the actual risk of your empirical allocation, of course, is subject to the real market, R here. That means you're using the true covariance matrix. And of course, you could simply, and again, it's not that difficult, you could derive some mathematical inequality among those 3 quantities. So basically saying that all those 3 quantities are close as long as the C, that is gross exposure constraint here is not too large, like 1 or 2. And in addition, that the components-wise estimation error is not too large. Now, of course, the natural question you may ask is how large can the components-wise estimation error is? Because C, you have a choice, right? So if you don't want your portfolio to be too extreme, you could C equal to 1, or you could C equal to 1.5. That means you have 25% short position, 125% long position. And so here, well, I mean, this is just really just a graph, so maybe I should explain a minute here. So this, what I plot here is the gross exposure constraint C increases, and the black line here is the in simulation I'm orgo, so therefore I will be able to plot the orgo risk. As you know that when the constraint is relaxed to certain points, so and the constraint is no longer binding, that is bigger than L1 long a Markowitz portfolio, then the risk will stay constant, right? And empirically, there's no reason why empirical risk has to be smaller than the optimal risk, but it's always more the case. Empirical risk could go all the way to zero. And this is the empirical decision, but put in the market, so it go down and then go up. And after a certain while, it's become a random portfolio because it's like a random choice of portfolio. So this is really the risk of a random portfolio. So our theorem basically saying those three lines are very close when C is small, and this is shown in this picture. So now the next one, so let me move on. The next one is how large the maximum component-wise estimation error, AN here, can be. And this certainly depends on dimensionality, how large the covariance matrix I'm estimating. The larger I should get, the larger. But basically, if you have, let's say, root n consistent for each element-wise estimation, and in addition, you have some kind of large deviation or concentration type of inequalities, then it just two sense mathematics, basically saying the maximum elements-wise error would depend on dimensionality in logarithmic order, and it's still root n here. So basically, the impact dimensionality is limited, but we really need, if you want to apply this, we really need large deviation type of result or concentration type of inequality rather than just usual central limit theorem. All right, so now let's go to the theme that the portfolio selection with dynamic covariance. So let's say our holding period is tau, and this is the return vector of your portfolio. So therefore, this is the return if I hold tau period. So if I write it into integral, it's like this. And the risk certainly would be just the same way. Now, this sigma is your conditional expectation of the future volatilities. So in other words, if you really want to know the risk of your future, you can really need to know, unless it's as long as the time varying, you are really involved in some kind of future forecasting of future realization path, if you like. And okay, so this is really stochastic volatility. And you could say the same thing, that you want to minimize the portfolio risk, subject to psi constraints, whatever you like, and then subject to gross exposure constraints here. So this is really the same thing as what we have before. Now here, what I have in mind is the portfolio is large. So this sigma is large. And I try to argue is that, well, unless you really know the dynamic, the parametric model, so as long as you use certain kind of non-parametric, you always have to have some kind of forecasting errors, or forecasting biases, and inevitably. So therefore, you really want your portfolio to be stable with respect to your estimation error. And this is really what we really use in non-parametric world, right? So so covariance matrix has to be predicted, so it's not estimated. You are really, not summarize the history. You have to forward-looking work in the future. And let's say if for the short horizon, so next week's average volatility, I could say, hey, it maybe can be approximated by last 2 weeks average volatility. So in this case, I really use continuity in my arguments. So because the continuity last 2 weeks average is about the same as future average. And for a long-term time horizon, so what is the average volatility in, let's say, 1 month or half a year, which is rare, but let's say 1 month? Well, I may say, well, is approximately the same as the average volatility in last 1 year. So in this case, you're really using ergodicity, right? So both of those hope you go to asymptotic things. So the argument here is even though that we observe, even though you have high frequency, you observe in every possible time point as detailed as you like, as high frequency as you like. Even if you fully observe your SU without idiosyncratic noise or whatever, your future has at best been approximated. And because it's approximated, you really want to reduce the sensitivity of this approximation, and therefore it makes a lot of sense to put a L1 constraint here. And why it makes a lot of sense putting L1 constraint here is because of these risk approximation theory make it possible that doesn't too sensitively depend on the error of the entire matrix, but only depend on elements-wise estimation error. All right, so now here I'm just focus a little bit, just help you put into perspective contrast between low frequency versus high frequency. So low frequency usually will refer to daily data. We're maybe using a year data to estimate volatility matrix. Right? So you are really estimating 1 year's volatility, past 1 year's volatility matrix, and you hope that this will be a good approximation of volatility matrix in the 1 month ahead. That which may be reasonable, okay. But if you're really estimating either for 1 day or 1 week, I mean this approximation can be very bad, right? Just like conditional variance versus unconditional variance could be very different. So therefore, it's not applicable to short time horizon, and it's only applicable to long-term time horizon when data is stationary, so and the ergodicity reasonably hold. And using high-frequency data, you actually have much more things, right, to say. Now you have far more data available for estimating covariance matrix, so therefore you could now shorten the time interval because variance being reduced. And once variance is reduced, it allows you to reduce the model approximation error. So therefore, you could reduce the approximation error. And certainly, you adapt better to the local market conditions. And of course, it could apply if any time you could apply low frequency, certainly high frequency, continue to apply with more computation cost. All right. So now this is talk about the estimation of high frequency using high frequency data. So I mean, by now there's a lot of studies on on high frequency data, and let me just go by quickly so that you could see something else rather than focus on this part. So there's certain microstructural noise errors, non-synchronized trading issues you need to deal when you're talking about covariance matrix estimation, and we have synchronization. Should I synchronize pairwise or should I synchronize among among, let's say, 1,000 stocks? So this is synchronization issues. There are jump in data. How do you need to remove jumps? And there are certain data cleaning issues in high-frequency data, and so on. So if I want to estimate the volatility matrix, and thanks to the theorem I just tell you a moment ago, that is the approximation error, the risk approximation error depends only on the components-wise estimation error. So therefore, I could really, in principle, estimate matrix components-wise, and this is very nice. Estimating matrix non-components-wise always too rigid. So therefore, we are let's decompose things into estimating matrix components-wise. Let's say diagonal elements. So diagonal elements is equivalent to saying that. So this is the latent price, and you observe data with microstructure noise. So I follow more or less Yasin Aisahali and his collaborators framework here. And then certainly there are one-scale, multi-scale methods. There are realized kernel methods. You could use wavelets method to detect jump and diffusion. You could use bipower methods to eliminate or reduce the sensitivity of jumps. And you could use quasi-maximum likelihood, a student of Yasin's, Shu, to do that. And you could use pre-averaging, just like smoothing methods, to reduce microstructural noise, and then you compute that. So there are a lot of methods. I'm not going to detail on that. But for mathematical convenience, I will focus only on the two-scale methods, TSRV. And I was just told that even Nicholas daughter could speak about high-frequency data, TSRV, because I think the families communicate so often that even the kids who maybe 3 or 4 years old now knows TSRV, so how popular it is. Okay, so so this is the two-scale method is very simple. So basically, you compute the realized variance based on subsampling, and now you have subsampling here. Now you just shift your subsampling. You averaging of many of those different kind of subsampling. You get the estimated at k scale, and this consists of 2 parts: the integrated volatility you want and microstructural noise you have there. And now you just take a simple adjustment. You got a TFRV, and it has been very nicely proved by my colleague and my friends, and Miklan and Yasin Aisahlia. So they basically saying that TFRV is asymptotic normal with exactly stochastic error specified by here. And so this is not adequate, unfortunately, for us, because we really want to apply not only one particular element, but uniformly across P many elements, like 1,000 elements or something like that. So therefore, we really need to expand their results and into the concentration type of inequalities. And so for large X, let's say X no more than 1/6, then we could show that TFRV has rate 1/6, but with the exponential tail when X is no more than 1/6. So now if you directly apply these kind of union inequalities or union bound inequalities, you could show that the diagonal elements can be estimated uniformly with the rate certainly is the slowest, traded stock, and then times the impulse dimensionality is 1/6. So now we need to estimate the off-diagonal elements. And if you want to do the off-diagonal elements, so you need to do data synchronization because stocks are traded in different time. And one of popularly used data synchronization is called refresh time. So let me not detail on this, but it's basically just you starting at 9:30 until first stock trade, and you put in the time here as they trade a synchronized trading of each stock, and start again, keep going, and this way. And then similarly, you could define two-scale CV realized covariance matrix covariance. And of course, there are other methods you could use too in principle, but theory probably needs to be derived. We only derive from TSCV, so I will just on emphasis on this. Again, it's because mathematical simpler. It doesn't mean that this method doesn't work. And then you could show a similar kind of results that, let's say this is the synchronized amount of data, 1/6, and we basically showed that TSCV is converged to your integrated covariance matrix and with those exponential type of tail, and this is usually called concentration equality. And let me skip the conditions. So now let me apply to portfolio optimization. So our portfolio optimization again is minimize the risk, subject just one extra constraint here. Gross exposure is no more than C, and the error is bounded by components y estimation error times C squared. And so we now in practical implementations, you have two ways to do that. One is pairwise estimation, components-wise estimation. So you could do pairwise refresh. So for each pair of stock, you wait until the other trade once, and then synchronize the trading. So so in this case, the rates of convergence, according to the theory, would be 1/6 of the minimum pairwise refresh time, right? And pairwise refresh time, the slowest refresh time, and then times the impulse dimensionality is log P. And the other one is that you could say, hey, let me just for 1,000 stock, let me wait refresh among all those 1,000 stocks. So this is I would call all refresh, right? So wait until every stock trade once. So the data is certainly you use much less data because you are waiting until the slowest person to get trade once. But then this sigma hat is usually semi-definite, positive definite matrix. So therefore, you are much easier to deal mathematically. And then the rate of convergence, according to what we showed there, would be n to the power 1/6 times n 1/6, so which would be the pairwise. All refresh time. So this one, and certainly it's a lot smaller than this one, but you could intuitively expect that's not much smaller. Okay, so now in practice, we have to twist a little bit because if I want to do optimization, most optimization software so far, unfortunately, requires sigma hat to be a non-negative definite matrix, and we have to do projection. So one of the simplest projection, you just take a non-negative part of your eigenvalues, but the other possible is that you are subtract by the minimum eigenvalues, and we use projecting to the main reason we are using projection. 2 is if you give me a correlation matrix, the diagonal element will be still 1 after projection. And but anyway, so the point is that once we do projection, elements or estimation error being distorted, and so on. So let me quickly go to just an empirical study to give you a picture. So this is 30 stocks from Dow Jones Industrial Components in the volatile year 2008. And I mean, even for those 9 months, we already got over 200 million data, and on average is maybe 10 trade per stock per data. And this already give me 13 gigabytes. 13 we were hoping we could do SP100 components, but just download data take a long time. And then in order to illustrate the points that low frequency work worse than high frequency, I applied the short holding period. As I said, low frequency is unconditional variance, doesn't work very well for conditional type of variance. And testing data is the 3-month period here. And so since we are using 15 minutes return, so this gives me more or less equivalent to like evaluate the data based on this amount of return data. And for high frequency, we use 10 days, and for low frequency, we actually only use 100 days. Actually quite short. If I use 1 year, I think the bias will be larger. And this is just the amount of trade that we have get, and this is really the empirical result based on 1 trading day. So this is low frequency data, and this is equal weighted data risk, and this is high frequency based on method, so which certainly have lower risk. And since my time is up, but this is the worst. How skewed the weight is actually for low frequency data. The weight among those 30 stocks is very skewed. And this is similarly for 5 days that low frequency data work better than, worse than high frequency data, particularly when growth exposure constraint is big and is unstable. So let me just quickly summarize a few words so that you know what I have been talking. So I basically advocate a portfolio selection with growth exposure constraints, and because this constraint is less sensitive to estimation errors, and you have little noise accumulation. And we basically propose high-frequency method, be either all refresh or pairwise refresh methods. We derive concentration inequalities and demonstrate limited impact of portfolio size. We use high-frequency data to increase sample size, shorten time interval, and adapt to local correlation. And we demonstrate the utility while simulation studies. Thank you.
Please visit us at www.atc.edu.